Good evening, everyone. Good evening. We'll make a start. Thank you for being on time, so we can start at 7:30, so we can get our full value out of Andrew tonight. Welcome again. I think Ralph. Welcome, Ralph. Probably, I think first time here. A couple of people in the front that we haven't seen before.
John Hayes.
G'day, John.
I'm the next Vice President.
Oh, welcome. And your name?
Sandra.
Oh, hi, Sandra. Oh, welcome. Any visitors or new members that I haven't spoken? Oh, it's brilliant.
Sorry, some late ones. Apologise.
There you go.
Oh, there you go.
Yeah.
No worries.
So before I introduce Andrew, after the break, Richard will be presenting on the night sky in November. Just a reminder, we've got a dinner for the South on the 14th of November. Information on the website and register. If you don't like using the electronic sign-in registering things, just see me at the break and I can put your name down. So that'll be the Telegraph Hotel. So it's supposed to be very nice there. This Thursday and Friday, Richard will be hosting the Night Sky Explorer course at Mount Pleasant. Probably looking for some more volunteers if anyone would like to come along. It's a fun evening with the people registered, and so use of the scopes or just talking to people about your love of astronomy. So there's two Night Sky Explorer courses each year. So that's generally on our website that we advertise. And also on the Facebook page. So if you link in, is it like, or join in with the, I'm not sure what it is with Facebook, but if you attach yourself to the AST Facebook page, then you'll be notified when that event comes up. So I think the next one will be about March, April this year. Yeah. And a good course, it's not just for the public, but for members and new astronomers. So it was a terrific introduction to the night sky and telescopes and all things astronomical. November the 18th, we've got the last astrophotography session for the year. Just a reminder that your homework are low northern targets, e.g. Andromeda Galaxy. If you fail to bring your homework, still come along. But if you have any questions, there's going to be a Q&A panel. If you've got any questions about astrophotography in general, you want to bring along some images and get some advice on how you could have improved them, then that advice will be forthcoming. I'm sure they won't be able to fix all the problems, but they'll certainly have a go. If you haven't put a ticket in for the Lucky Door prize, we have two prizes. So no expense spared this month. We've got a beanie, there's one prize, and a star disc. So if you've gone electronic and you don't want a star disc, this will be a great Christmas present for a son, daughter, nephew, grandchild. You got frisbee, or turn it into a frisbee. Yeah. Thanks, Mark. So I'll introduce Dr Andrew Klekociuk, who has been a member of the Society since 1974, and I think it's just terrific that we have such long-standing members that continue to contribute to the Society. They have a depth of experience, and we really value that experience. And there are a few other notables in the room that would share that with Andrew. Looking back at, and Andrew was very kind to donate a whole swag of bulletins. So the bulletins were was the magazine of the Society. I wasn't even aware that they existed, so I just started something called the newsletter, which is pretty boring. But when I look back at the bulletin, there's a swathe of dedication that went into that publication over the years, and I think somewhere about the high 200s of actual numbers of the bulletin were published over the years. So Andrew's donated quite a few. I'm going to list the ones that we have in the next newsletter. So if you're having a clean-up, have a look for any old bulletins that you've got. Steve Harvey also donated some to me. So the eventual home for those will be, once we've got the catalogue, what we have is to take those to the State Archives. So they're there forever, basically. Anybody that wants to have a look at the historical sort of events of the Society, they can go back and have a look at those bulletins. So Andrew is going to talk to us about things that go bump in the night. I'm really interested in this because he's summarised it by saying that he's doing a lot with little in terms of getting off-the-shelf electronics to be able to help him with his science. And although he's retired, he's still continuing in science and detecting meteors, comets, all sorts of events in deep space and also in our solar system. So I'm looking forward to this. Anything to do with space physics, I'm really interested in. Without any further delay, I'd like you to welcome Andrew to present to us.
Thanks very much, Ross, for that kind introduction. I'd like to welcome my colleague, Professor Gennady Milanevsky from the Ukraine. Gennady and I have had a long-term collaboration going back many years. Gennady's an expert in space physics and has done a lot of work with me through the Antarctic Division, and he's has the honour of being the first base commander at the Nadsky, which is the Ukrainian Antarctic station in the Antarctic Peninsula, which was handed over from the United Kingdom to the Ukraine, and a really fantastic station which continues research, and the Ukrainians are there at the moment still conducting research, which is fantastic. And Gennady's in town for the CAMELAR meeting, the Commission for the Conservation of Antarctic Marine Living Resources. So thanks very much, Gennady, for coming along tonight. And in fact, some of the things that I'll show you here, Gennady and I sort of work on a little bit, and it's really helped. Some of the devices I've acquired at home, I've actually used in my research in the Antarctic. We've kind of proven things at home and then done some work to extend them to the Antarctic. So it's great to have Gennady here tonight. So in my talk tonight, I'm going to sort of take you into the world of sensing things that happen while you're asleep mainly. And I'm quite keen on doing 24-hour, 7-day-a-week astronomy, but I don't want to be at the eyepiece all the time. So I employ some cameras and other sensors to try and detect things. And there's an amazing number of, an amazing variety of things happening in the night sky, and we'll talk a little bit about some of these here. So a bit of an outline of tonight. I'm just going to give you a glimpse back into my childhood to explain why I'm the way I am, but where I came from. But then we'll go on to having a look at 3 areas, one of which is some systems I have to monitor the sky. I'm lucky I have a small rural property down at Kingston, which gives me a bit of room to put sensors out, and I've established some devices away from my house to get rid of interference, but cameras, sky monitors, all sky cameras, and webcams that I've modified to see things happening around us. I also have an interest in meteor astronomy through my career in the early days of my career in radioastronomy, and we'll talk a bit about detecting meteors with some simple equipment you can buy off the shelf, and then on to using some other types of antennas to look at things happening on the sun and even at astrophysical distances, gamma ray bursts. And importantly, how can you make a contribution to this area? How can you actually use your data to improve knowledge? So this picture here is actually back a few years back when we had nice sunrises produced by the dust from the Hunga Tonga eruption in the Pacific. And there was a period there where we could see these beautiful coloured sunrises, but some structure you might just discern in there. There's Jupiter over there, but some fine layers. Now the connection there is that probably one of my earliest memories is of the Mount Agung eruption. That's an Indonesian volcano which threw a lot of dust into the stratosphere in 1963-64. Now I was about three years old in 1964. Now the reason I can remember that is that my dad used to take me out to feed the chickens in the morning, and he said, "Oh, this is an amazing sunrise. The volcano did that." Now the other connection there was that in that year, my grandfather on my mother's side, Ernest William Reed, and my middle name is Reed, I take my mother's family name, he passed away. 1891 to 1964. And my mother bought me this book called Grandpa Bunny, and it was a Disney book. The connection there is that when Grandpa Bunny passed away, he went into the sky and produced these beautiful sunrises or sunsets. So that's the mental connection I have. So that's how I can remember that. I can remember Mount Agung back in 1964. It was about January, February 1964. And we've had a few of these. Mount Pinatubo was another one that we saw from Kingston. Now that sort of sparked my interest in things environmental. And we'd get up in the morning and look for planets. And my brother bought a book exploring the planets, which told you when the planets would be visible in the sky. It had a little almanac in the back. And my father here, and that's me, back in 1974 at an AST event. This is the year I joined the AST. My father knew Ted Schultz, who made telescopes. Dad and Ted were in the war together. Ted came out and worked on the hydro with my dad, and so we ended up making a telescope. My dad did all of the mechanical stuff. Ted showed me how to grind a mirror. So this is way back in the day when we were out looking for Comet Cohetek. Back in the day, there's our young Martin George, if you are wondering who that is. And Bob Watson from university, Colin Bisdee, who used to produce the bulletins back in the early days, which Ross has got some copies of. Elizabeth Hickman, who was a member, and a couple of other folks there. And this chap, we think, is from the BAA. And Chev Mathers probably took the picture, and we're trying to track down who he was. So if Chev's out there, you might remember. Now, around that time, as a young kid, I discovered music, and I discovered the Moody Blues, and I loved the Moody Blues. And this poem by Graham Edge from In Search of the Lost Chord really inspired me, because it sort of summarises, you know, kind of things I'm interested in, trying to perceive things that are out there. If you get a chance, look that one up on Spotify or something like that, and listen to the words. There's a whole range of other interesting things about the Moody Blues, but that for me kind of also captured some interest that I have. And so I went on to think about how I was going to measure things. I had some sky and telescopes which told me a bit about meteor astronomy and solar flare monitoring. Told me a bit about the American Association of Variable Star Observers. So I set up some gear in my mother's backyard, monitoring solar flares and contributing to the AAVSO, American Association of Variable Star Observers. So I was a member of the AAVSO from sort of the about 77, 78 for a few years, and did sunspot counts and solar flare monitoring and variable star measurements with the naked eye. But after that, I had a bit of a hiatus when I sort of finished uni, and I didn't come back to actually establishing, I guess, measurements in my backyard until the 1990s. And I'll show you a little bit about some of the earlier stuff. But in the last few years, I've set up some instruments to measure the night sky brightness, something that I was interested in. How dark is it really at my site in Kingston? And is light pollution changing? So I bought one of these sky quality meters, and folks might be familiar with these. There's a network of them, and they contribute to the dark sky activities. And relatively inexpensive. It's basically this device here in a weatherproof enclosure. It's just basically a photometer that measures the brightness of a cone of the sky centered on the zenith, in the case of this one, which is pointing vertically, over the visible range of wavelengths. And that sits there. That's been running for over 10 years now. And it's on this pole here, which the sheep, I've got a few sheep that like to rub on it occasionally. Somehow it survived. And I've got a USB repeater with some Cat5 cable over a 100-metre run, goes back to my shed. It's one of these repeaters that's actually powered by the USB, so I don't need to run a special power cable. So there's basically just a USB cable, USB connection coming back. And on that pole, I've got not only the sky quality meter, but an all-sky camera. And I've had some webcams in there. And then here, in this device here, I've got some infrared sensors looking at the sky and the ground to measure cloud, as well as I've got a string of sensors in the ground and things measuring the soil and moisture and a few other things. Sometimes the sheep get in the way. Now, there's plenty of light pollution out there, we know from the cities, but there are other natural emissions. This is the aurora, so this is an image from the Suomi polar orbiting spacecraft. It's got this visible and infrared imaging system which takes low light level images, and that data is available online. You can go and have a look, and often you'll see the auroral oval. The satellite is orbiting the Earth every 90 or so minutes, and it's processing, well, the Earth's sort of rotating underneath it, so it's seeing a different range of longitudes. But it's amazing when you look at these images how much light pollution there is in Hobart, and you'll see lights in Bass Strait and other interesting features. Savage River is a very bright feature. So I was kind of interested in seeing if I could, first of all, see maybe a growth in light pollution, but also detect things like the aurora. So here's some results. So I've been measuring, as I mentioned, for about 10 years, and that's long enough to actually start to see some trends. So this is a summary of the measurements. It's calibrated to return a value every minute, measured in magnitudes of stars per square arc second, tiny patch in the sky. And interestingly, when it's around about nautical twilight, that's around about sort of magnitude 8 or 9 magnitudes per square arc second, which is kind of an interesting threshold. But here you can see over the course of 1 year, I've got pretty good coverage. The odd little glitch when maybe there's a Windows update and my computer needs to restart itself. I've just been battling with Windows updates today on some systems. But the brightness of the sky varies, of course, for a number of reasons. Now, interpreting these numbers, so darker is actually a larger number. So where it's orangey coloured here, it's actually a darker night sky. And when it's a smaller number, this is where the moon, the full moon, pops through each month. And there is some mottling in here because it's cloudy occasionally, and when there's clouds, it reflects the light from Hobart and surrounding suburbs. So kind of an interesting pattern there. When we dig a bit deeper into it, here's a bit of a summary. I've put a dot for every measurement, and I've sorted this according to solar azimuth, so the azimuth of where the sun is around the horizon. I've also picked times when the moon is not in the way, essentially. And the interesting thing about this, so as the sun sets, it moves around through the southern part of the sky. So the azimuths actually decrease as the sun moves around the sky. I'm not showing you where the sun is in the daytime sky because the instrument's actually not, it gets saturated during daytime. But it really is, if you interpret this, as the mamas and the papas said, the darkest hour is just before dawn. So these numbers increase here. This is actually going from sunset to sunrise. And the reason it's doing this is that there's air glow in the sky. So a natural chemical process happening in the upper atmosphere, which is energized by the sun, which gets quenched during the night. And so if you really want to get the darkest period in the night, you kind of wait till the sun is around about due south, kind of midnight. And then all the air glow is pretty much gone. So that's kind of an interesting thing if you're really after the darkest sky to get your deepest images. And then another interesting thing is that when you look at the transition from day to night around the dusk period, dawn or dusk, and you plot this, all the data together, you see some interesting kind of changes during the year because the width of the terminator, the day-night terminator, actually changes with the seasons. And this is actually telling you something about that. We'll dig a little bit deeper into that one in a second. So digging a bit deeper here, I've plotted, these are the darkest measurements, essentially, throughout the year and for all of the years I have. And if you're kind of wondering why there's a dearth of things here, this is actually the Milky Way, is brighter than the limiting magnitude which I've plotted here. So the Milky Way actually kind of moves through this part of the sky. These are for Bortle 3 conditions. It's probably about what I get at my place. It's Bortle 4, maybe. But yeah, I can detect the darkest points, and these are the ones I'm really interested in, particularly at this time of year where if I was to take any measurement throughout the night and just look for the darkest ones, it might give me some indication of trends. So here are all the darkest ones plotted now as a function of time of year. And you can kind of see this sort of pattern happening. So this is all these measurements just sorted according to year. Sometimes we get some really dark skies. Now, with my camera, I can go and check to see if the sky is clear. And in fact, these are clear sky occasions. So we do sometimes get some very dark Bortle 4 type conditions, at least at my place. Maybe there's a power failure and all the lights are out or something like that down at Kingston. A bit of a gap in here. The famous 2018 storms that we had. If you remember the torrential rain, May 2018, it knocked out my senses for a while. And it took me a while. In fact, it was the lightning. Remember, we had a lot of lightning, and I had some lightning strikes nearby, and it actually fried my my USB device. So that's why there's a bit of a gap there. But what you can see here, if you look, there's a bit of an envelope, and in fact, to interpret this, you'd basically say that darker skies are up here. So there was a period where it got dark, and now it's getting brighter. And we'll look at that in a little bit more detail here. Now I'm just picking out September, October, November, which is that period where any time of the night there's a dark period. And you can kind of see a bit of a trend in there. And this kind of surprised me, but maybe not. I was expecting the solar cycle to have an effect, and So I'm taking the average for each year, and that's the blue, these blue values with error bars, that's the sort of standard error on them. And they're well correlated with the sunspot number. So what's happening is that as the solar cycle goes from minimum to maximum, the amount of air glow in the sky changes. And so the sky is brighter during solar maximum than solar minimum. Now I thought maybe I'd see urban growth or changes in light pollution. But I reckon the solar cycle's got a stronger effect on this, and I can't see any evidence of a strong trend. Now, there's probably a weak trend in there. I might have expected maybe during COVID a bit of a drop in light. It's a bit complex in my place because it's not just the glow from the horizon, it's got to scatter up to the zenith and back into my device. I've got the southern outlet, or the Channel Highway, or Huon Highway I should say, nearby, so I was thinking maybe it's truck changes, but I think the solar cycle's got the biggest effect there. So on to the camera. So the beauty of having the camera is you can check what the sky conditions when you've got your light level measurements. And so I have with this All Sky Cam device, unfortunately you can't buy them anymore. Really quite a sensitive device. In fact, the All Sky Cam has a sensitivity of 0.00002 lux. And the next best thing you can find at the moment for a video type camera is this RunCam, which is a bit less sensitive. The reason I like the video cameras is they can pick up really short events. And in fact, in principle, you can get a frame, you get 30 frames a second out of the video camera for the whole sky, and things like a Starlink train going overhead. See many of these going through the system, quite easy. And even at sort of, this camera actually stacks a few images together to give you this image. You get down to that magnitude 5 limit. So it's kind of similar to the naked eye. You can see here these flashes, these are cars and trucks going down the highway. So I have to put up with that, and that's the glow of Kingston and Hobart in my area. So you can have a look at this page. I keep that going. I've had a few sensors fall out of it, but I made this display using ImageMagick and AutoHotkey, two open source bits of software which enable you to stick things on tops of images. Really quite useful, and I do a bit of scraping, legal scraping of the Bureau's website, and even with the Bureau's changes in its website, the radar and the, at least when I looked yesterday, the radar and the Space Weather Service's auroral KP index for Hobart area, still there. And I grabbed this one from the Brisbane Storm Chasers and from NOAA, the auroral oval, just to give a bit of a picture. And there's a little circle here which tells me if the aurora encroaches within that circle, I'm likely to see something close to the horizon. In this case here, it's sort of just on the southern horizon here. So you can have a look at that. The other cameras I've got, I had a webcam in here looking out, that was the infrared camera, and then another camera I still have which looks to the west. And a few years back I picked up this smoke trail, if people remember that, over Hobart from a Russian rocket re-entering. We see that sort of thing sometimes. Now, sort of combining a few things together, so that the camera is good and it produces this keogram. So it's the north-south column of pixels then displayed as a function of time, which sort of gives you a slice through the meridian. And going from south to north, the zenith's in the middle. And here's an auroral display back in 2021. And then I can compare that against my sky brightness measurements, and we get some indication that we're actually even able to detect aurora near the zenith. with this device, and then get some quantitative information about how bright it is. It's very broadband, but yeah, it's kind of an interesting thing. I really haven't done anything with the auroral stuff there, but at least I can sort of verify that these features are probably aurora. They're not cloud. See here, star trails. The sky's quite clear. And then getting some interesting numbers on lunar eclipses. Here's one back in 2018. This is the sky brightness, and I've displayed it here so that the number, larger number, this is darker sky down here, brighter sky here. This is the measurement of brightness, and I've put some lines in here for partial and total phases. And here's totality, nice flat line, so the sky is darkest during totality. In this case, the moon was quite close to the northern meridian around this time. So gives you some idea of how bright the eclipse is. And the interesting thing about this, if you take note of the number here, kind of around about 21.2, so quite dark sky, sort of getting down to Bortle 3, I suppose. This most recent eclipse was not as dark. So the moon was a bit brighter. Now, back in 2018, there was some volcanic aerosol from Calbuco, which was a Chilean volcano. We had a gung, not a gung, we had Hunga Tonga in 2022, but the stratosphere's cleaned out a bit since then, and I think that's part of the reason that the sky was just a bit brighter during this last eclipse. And here's the keogram again, showing it's kind of clear through that period. A little bit of cloud on the southern horizon. Some of these little blips here are just catching some of this light scattered from that. Now, I posted something in the AST imaging page about the brightness of the moon. So I had an all-sky cam picture with some stars, and here's the moon over here. And I was wondering, what is the magnitude of the moon? And I thought, well, I can do some photometry with my camera. And it's kind of like, this is the first photometer, the Bunsen photometer, which is actually, you can make one of these at home. You get a sheet of, I guess, lunch wrap. Not the greased one, but you want to put an oil drop in the middle of that, put a light either side, and you adjust the distance of the lights until the oil drop disappears. I mean, that means you've got the same brightness on either side of this piece of paper. And that's how the early astronomers actually, before the invention of photoelectric cells, before the photoelectric effect was discovered by Einstein, actually made estimates accurate estimates of the brightness of candles or standard lamps, and then use that to try and estimate the brightness of stars. Now what I'm doing here is I'm comparing the moon against some standard candles, which are the stars in the Milky Way. And I asked Copilot to help me. And what Copilot, I had to train it, but I got it to write some Python code for me, which just put a box around the stars and gave me the brightness of them averaged over the boxes. In fact, it gave me, I had to get it to give me the upper mean, so that's the average of the brightest 50% of the pixels, and plot that out as a function of the magnitude of the stars. Now, what I've done here is I've identified the stars. So they're the numbers of them there. You can sort of compare them against the plot there, and here are some well-known ones. And I'm doing this in the red channel of the camera. So there's red, green, blue. They have broad spectral bands. And the red channel in my camera is actually similar to the photometric R band, the Johnson R band. around about 610, 620 nanometers. And in the R band, Aldebaran is actually the brightest star in the sky. It's not Sirius. It's Aldebaran is about magnitude minus 2.2 in the R band. A bit hard to tell in here because this is RGB. Canopus and Sirius are still quite bright. Betelgeuse down here is actually, even though it's a red giant, it's still, relatively similar to its visual magnitude. But I get this nice linear relationship, and what I've done here, I've also corrected for extinction in the atmosphere. So take the elevation of the object, calculate how much atmosphere is between me and the star, and then adjust the brightness of the star accordingly. So it produces a reasonably good relationship, and here's my estimate of the brightness of the moon. Magnitude minus 1.2 plus or minus 0.5 magnitudes. And that turns out to be a fairly typical lunar brightness, a little bit on the brighter side, not as dark as some of the volcanic eclipses, but I discovered in doing this, I said, oh yeah, I'll go and compare against, a few eclipses and tell you a bit about that. Well, hardly anybody has really at least done photometry in different bands. So there's actually an opportunity for an amateur to actually look at some other eclipses, and I'm going to go back and look at 2018 and see what that's like. I should be able to do that at least with my camera. So that's just an example of what you can do with some photometry. Another thing I have, as I mentioned, the infrared sensors. So I've got these devices looking at the ground and the sky, and when there are clouds present, the sky is actually warmer. The clouds are warm bodies and not as cold as free space. So here I'm plotting the brightness. It's actually the difference between the ground temperature and the sky temperature as a function of time, and comparing it with my sky quality meter, and there's a very good relationship. The good thing about this infrared device is that it's not affected by dusk or dawn. And so this record I have of over 10 years now, I can get some really good statistics on sky transparency and cloud cover. This camera, this all-sky cam, after we bought this, I developed a program in the Antarctic to measure the amount of cloud at our Davis station when we were making LiDAR measurements. And we developed an algorithm to actually extract the sky fraction. So if anybody's interested in how much cloud is over Kingston, I can tell you quite accurately. It'd be nice to, if you, maybe at the observatory, we could set something like this up, and you could actually then even get some indication in real time how transparent the sky is. That's using a Leo stick USB device, really simple, just a USB plugs into your computer. Three wires for each of these sensors, and you're away. A little bit of code you can write yourself. Now, on to some other things that I've picked up. So, very bright meteors, bolides. The brightest of the meteors are called bolides, and these are the ones that are likely to fragment and drop stones on the ground to become meteorites. So here's one back, 2016, early days of my camera, and on the horizon. Back in the day, I was taking images. This camera's quite good. It's got a motion detection feature, so it will actually save subframes. And so these are subframes about 4 seconds apart, showing the motion of this bright streak in the sky. And lo and behold, some folks locally managed to see it. And these observations are logged in the IMO, International Meteor Observing Network. You can go and look these up. I look at these from time to time just to see if I can find things with my camera. So these camera measurements are useful if you want to try and, between a number of sites, work out where maybe some meteorites have landed. This event here, probably, I'd say it's 50-50 whether it was a real bolide or a satellite re-entry, left a big streak. When I was running the camera in these days, I was taking measurements every 5 minutes or so I don't get individual frames, but it did a 5-minute average. So this is kind of a streak. I don't quite know how long it was in the sky, but there's a description from a mate of a jockey out at Brighton that said it was slow moving, but it was moving much faster than a satellite. It was only in the sky for literally seconds. So I reckon it was a meteor bolide, and it went in this direction. And this guy said, I heard something after it. And I have when I put my camera and other sensors in, I thought, I'm interested in infrasound. It's the sound that you can't hear with your ear. And I bought this device, an Infotech infrasound device. It's a bit like attaching some really big saucepans to your head. Actually, this is a serious photograph. These were used during the war to pick up aircraft, the infrasound from aircraft coming over the horizon. I might try and whip one of those up at some stage. But yeah, so this is just a USB device, a couple $100, and lo and behold, on this particular event, there was a bit of a bang. And the timing of this bang actually corresponds with when this thing was seen, suggesting a speed of sound 300 meters per second from Brighton. So there was some sort of bang. I'm not quite sure what that is. The other thing that with this device, it's like a microbarometer, so it measures very tiny pressure changes, and things like rustling leaves and tree branches cracking and my water tank, something dropping onto that makes other noise. And actually, the interesting thing about this background here is that when you take a Fourier transform of that and look at the periodicity, I'm actually seeing the waves crashing on Kingston Beach. So there's about a 12-second periodicity here, and I can see the swell. I can actually tell you what the swell is at Kingston. So if you're into surfing, these things are kind of interesting. Yeah, I don't know what that is. Then I looked at, you can go to this NASA site and see where all of the big meteor events occurred around the world. And there was a very large meteor event here, 1.6 kilotons of TNT equivalent, a rock a few meters in diameter coming through the atmosphere. I knew about this because back in 2004, we had seen something like this in the Antarctic, and I'd actually made the first measurements with a LiDAR of the dust trail of one of these events. The one in the Antarctic was much bigger. It was about 10 kilotons. So there's that one there. I thought, well, can I hear that? Can I pick that up with my gear? And lo and behold, on that particular day, the background noise was relatively calm, and I got some bangs from that event. And when I look at I filtered this to the approximate period. So this class of object produces ringing in the atmosphere between 1 and 10-second period pressure waves, and I've filtered that for that period. And the arrival of these bursts correspond to different speeds of sound. And it's interesting that as you go up in the atmosphere, so the fastest speeds are in the lower part of the atmosphere. And as you go up in the atmosphere, the speed of sound drops as the air becomes less dense. And so these are bangs produced near the surface, probably around about the tropopause, so about 10 or 11 kilometres, and then in the stratosphere. That previous event where I had the 300 metres, that was actually a stratospheric signal that we saw from Brighton. So these are bangs coming from explosions at different heights. So that's something you can get out of these devices. And then that brings me to meteor astronomy, because now I've got a camera and I've got some infrasound. Can I see radio echoes as well? So this is a bit challenging. It took me a long time to actually detect meteors with radio, because what I'm doing is I'm using a transmitter that's some distance away, and as the meteor enters the atmosphere, it leaves an ionised trail in the lower ionosphere which reflects the radio signal over some distance. Now, typically 200 kilometres to maybe 2,000 kilometres is a good path length between the transmitter and receiver. And I'm using a small radio receiver. There are other low-cost devices that you can buy. A fairly simple antenna, off-the-shelf antenna, and without any preamplifier in this case. So I'm just monitoring continuously at a certain frequency of this transmitter, and every so often you get a little blip, a ping, as a meteor trail appears somewhere between you and the transmitter. And free software that logs this, and these echoes are counted. And in principle, these also show something about the speed of the meteor. When the plasma trail appears, it can be blowing in the wind and can be Doppler shifted. So the frequency of the transmitter can be shifted up or down depending on the relative motion. So I've been counting those for quite a few years. And here's a few more examples. When you're listening on the radio, just a little ping noise. They only last literally sometimes a fraction of a second, producing these interesting trails. I don't see the transmitter continuously because I've got mountains, I've got the plateau between me and the transmitter, so it actually has to come off the ionosphere. At these frequencies, it's really ionisation that causes that. You can see sometimes if you use other modes of transmission, this is a beacon by the Cradle Coast Amateur Radio Group at around about 50 megahertz. There are a number of these amateur beacons around to look at propagation conditions. I'm just sort of using one of these. Back in maybe 20 years ago, you could use things like the VHF TV, analog TV signals, but they've all disappeared now. So it's really these beacons that are about the only means at the moment. There are other amateur modes of transmission. This is called Whisper, trying to make low power connections between sites. And sometimes you get a little ping when somebody's transmitting a long way away, and it just happens to catch a little bit of scatter. Aircraft are another interesting feature. So aircraft between flying, well, anywhere around central Tasmania, it might be the flight from Auckland to Perth, or it might be even sometimes I see aircraft going from Sydney to Santiago, come down this way. You get a Doppler shifted signal. Now the transmitter is normally just producing a single tone, but every so often it produces an identification signal, and that's why it's kind of spread out here. But this is an aircraft scatter, but maybe with a meteor ping in there as well. So you've got to kind of filter those things out. Now here's a little movie of a month's worth of echoes. So this kind of gives you an idea. This is October this year. It's actually a day in October. And these are the little pings in here. Sometimes the transmitter's just faintly visible in the background. And you get all sorts of different Doppler shifts, lengths of meteor, and some of the little flashes you might have seen as the background brightens, solar flares or local interference blatting the screen. But this software is quite good at picking them up, and then we count them. Here's some examples. I'm quite interested in receiving photographs when people see bright meteors in the sky, because I can go back and have a look at my radio detection or my all-sky cam. So here's a bright meteor that produced a trail over here and another one over there. Basically, the transmitter is in the northwest of Tas, so somewhere between sort of north and west is the best area for me to pick up these things. If they're too low on the horizon, particularly in the east, I can't see them. So it's this sort of backscatter that I'm getting. So the transmitter is actually scattering towards me. It's actually forward scatter, as it's called. Here's a bright one which produced a flash in the middle. And I've recorded this at 2 different frequencies. And the interesting thing here is that there's a bit of a delay between these two. I've put a line where the meteor occurred in my camera. This is actually an integration over 1 minute up to 1644. So it's actually an average over this period here. So the meteor sort of happened in there somewhere. And a bit delayed. It's quicker at the higher frequencies and a bit longer at the lower frequencies. And that's to do with where the ionisation is happening in the atmosphere. And in fact, sometimes it's the motion of the ionisation along the path that's important. It's a bit hard to unscramble some of this, but there are some interesting delays there. So I contribute to this radio meteor observing bulletin. I'm the only Southern Hemisphere side at the moment. Sometimes somebody pops up in around sort of New South Wales area. There are a few folks that used to pop up in Brazil, but they've turned off the analog TV stations there just recently, and so they've disappeared. It's just this little path that I've got is actually quite good, and these folks in the Northern Hemisphere, particularly in Europe, are using a space radar in France, and some other folks in the US are using beacons, but produces this little sky map. And you can go and look at these things. Here's a collection of observations, July, August this year. So this is universal time running vertically, day of month across here. And so these are the number of detections I'm getting. And I can see meteor showers with these things. And here I've plotted the average over the course of a day in different months. And if you read one of the recent AST newsletters, I described a bit about this, which relates to meteor showers, but also the Earth's movement in the ecliptic. And basically, there are meteors out there. The sporadic meteors vary in intensity throughout the year. And you can read that article, and I explain a little bit about that. I've got some quite good statistics now and good repeatability from year to year. So here's an average, sort of around about midnight, of meteor counts throughout the year, 1 point for each day. And I'm comparing 2024 to 2025, and you can see that the points overlap quite well, and we get some peaks popping up in both years. And in this case here, this is the Alpha Capricornid meteor shower, a little bit stronger this year than last year. So now with multi-year observations, I can tell you something about the strength of meteor showers. But the comforting thing is that the sensitivity is quite stable, and that's, I guess, another message. You don't want to be mucking around with your gear too much. You just want to set it and leave it. And here's another time of day. The Delta Aquariid meteors just recently were coming through. You can see I get quite a lot of counts, 50 counts an hour. Now, you won't see that with your eye. You might see maybe 5, but this is much more sensitive than your eye or even a good camera. Yeah. So some of this is actually the what's called the anti-Helian meteors. So this is the dust in the ecliptic plane that the Earth moves through. So it's not necessarily a shower, just the background of meteors as we go through. Best seen just before dawn, this anti-Helian. So that last part now, on to perhaps a different area, building on the radio stuff. And here I'm going down in frequency to the lowest frequencies, the VLF, very low frequency realm, which is used for submarine communication. Now, this guy up the pole here back in 1862, working on a telegraph, that's when people first started to hear things that were propagating at very low frequencies in the, what's called the Earth ionosphere waveguide, so between the surface of the Earth and the lowest ionospheric layer, picking up lightning propagating at very long distances. At these frequencies, lightning propagates almost unattenuated around the world, so you can actually hear a lightning strike in Brazil, or maybe it's in the US or something like that. And by measuring the time of arrival of these strikes at a number of different sites, you can do the lightning mapping, which you might see the Bureau of Meteorology. I've got a little station that I contribute to the Blitzertongue, which is German for lightning. And that's a separate thing. So I'm interested in lightning, but this part of the talk's just about picking up solar flares. So at these very low frequencies, transmissions from sites that are trying to communicate with submarines propagate very long distances as well. And submarines that are within maybe 100 metres of the surface can pick up these very low frequency waves, and there are a number of these naval transmitters. Started during the 1950s, but very useful for monitoring solar flares and gamma ray bursts, as we'll see. Now this is a loop antenna that I have. It's got two loops, the north, south and east, west. And by comparing the signals, I can actually also do direction finding. So I could tell you where the lightning was coming from or which transmitter was transmitting. So that's actually direction finding. So I started back in that photograph I showed at the beginning, back in the 1980s, I was doing this with a chart recorder. And then I graduated in the early 2000s to using the modern computer, the 386 Windows. Well, I started with Windows 95, so it was back in the late 90s. And you can use a sound card. So the audio card you might have in your computer for sound measurement, you can plug one of these antennas and a preamplifier in and then get a spectrum, which you can then isolate the transmitter you're interested in. So this is Northwest Cape in Western Australia, 19.8 kilohertz. Measurements over each day. There's a diurnal variation as the height of the ionosphere goes up and down, changes the signal propagation. The transmitter's off sometimes for maintenance. Hopefully we don't get a nuclear war when it's off. That's why they sort of schedule different transmitters to be on, just in case. These things actually transmit the launch codes for missiles in submarines. So not that I can tell you what submarine they're talking to, it's all encrypted, but having these things operating tells you that there's still submarines out there. And I presume we'll be doing that with our nuclear submarines when we get them, if we ever get them. That's right. These transmitters are extremely powerful. Like the one at Northwest Cape is a megawatt of effective radiated power. So it's got a huge infrastructure behind it to keep powering it. Not good for greenhouse emissions, I think. But anyway, so from time to time you get little blips in the signal. So this is the actual measurements of signal on different days in October 2003. Occasionally you get these little blips. This is back during the last solar maximum, and these are solar flares, solar X-ray flares that enhance the reflectivity of the ionosphere, and you get these signatures which correspond quite nicely to changes in X-ray emission. So this is a satellite measurement of X-rays. This one here, for example, you can sort of see quite nice. So it's a proxy measurement of solar X-rays or solar shortwave extreme ultraviolet emission. So it's kind of, that's why the AAVSO was interested in that. They were making measurements before the current batch of geosynchronous solar monitoring satellites were up there. And if any of those satellites fail, this is the best way we've got of seeing X-ray flares. Now, those little blips are one example of what's called a sudden ionospheric disturbance. It's a sudden enhancement of signal, but there are other sorts, and I've got a few different varieties here. So I monitor at different frequencies with different techniques, and at high frequency, This is a measurement of the time signal station WWVH. You might have heard that. Back in the day, that was our timing method, not GPS. You'd have a radio, you'd pick up WWV, it would tell you what time it was. You'd have second ticks, and you'd use that to look at things like occultations. I monitor that, I monitor the frequency of it, and when there's a solar flare, extreme ultraviolet flare, it produces this deviation in the frequency. At the same time, that will cause a dropout in the signal strength, a shortwave fade out. At VLF, the sudden enhancement of signal, so the amplitude of the signal goes up. If you measure the phase, so a wave is varying sinusoidally, but if you can time when the peaks come, there's a change in phase during a flare. As the ionosphere moves down, the time of arrival of those signals shortens. So it gives you some idea of the height of the ionosphere. That's a sudden phase anomaly. And here's the X-ray emission. There's another sort which is called sudden enhancement of atmospheric. So if you're listening out for lightning, you'd actually see an increase in lightning strength from distant lightning sources. Same thing, it's basically the ionosphere becoming more of a reflector. And Colin Bisdee got me into this. That's where he was, back in the day, he was monitoring SEAs from down here in Lower Sandy Bay. And that's how I got excited by that. And the other thing you can do with these high frequency measurements, the WWV, they are also sensitive to magnetic disturbances. So when there's a geomagnetic disturbance, the ionosphere kind of rings, and it actually becomes what we call birefringent. It changes the way that radio waves propagate. Radio waves get split into two polarizations and propagate with different speeds. And here's an example where this WWV signal all of a sudden goes a bit wobbly in frequency, and that's when there was a start of a geomagnetic storm. And you can actually time these quite well. There's quite a good correspondence. If you're listening to WWVH at the time, it becomes quite warbly and distorted. So one of the things I used to do back in the day was to have my radio receiver running in the background if I was looking at aurora, give me some idea if there was an aurora out there. This other little thing here, back in 2003, there was the brightest solar flare ever seen at X-ray wavelengths. And I just happened to be monitoring a whole bunch of different stations, some of them in the daytime hemisphere, which is kind of over here, some of them in the nighttime hemisphere. And here's a bunch of my nighttime hemisphere measurements, and here's my daytime hemisphere. Some paths actually sort of just cross the terminator. But on two transmitter paths, I saw this very big increase in signal strength. But lo and behold, the satellite got saturated. And so you could actually use these measurements to back out an estimate of how bright this flare really was if the satellite didn't get saturated. I worked that out, and I contacted some colleagues and said, I've got a number. And they kind of forgot about the fact that I'd sent them the information and did their own calculations and produced something very similar. It was the X43 solar flare. If you're familiar with the X-ray classification, when I back out the number, I get something quite large. But I kind of missed out on putting that into a scientific publication. And then more recently, other things you can do with VLF, monitoring the effect of solar eclipses on the ionosphere. So here's 2023, I'm monitoring this station at Northwest Cape. Here's the eclipse path. Totality went right over the top of Northwest Cape, and comparing against 2 different days, a little bit of a bump in the amplitude of the signal, but a big change in the phase, which tells me that the ionosphere actually went up in height. As the sun set during the eclipse, the ionosphere kind of healed, disappeared, and the signal indicated that it was reflecting from a greater height. So you can kind of get some idea of eclipse effects. People have done this for many years. Some other little solar flares happening which cause little deviations, even some close to totality. And then finally, another topic which is a bit more of a challenge is picking up gamma ray bursts, because they also produce hard radiation, X-ray, more gamma rays, of course, because they're gamma ray bursts, but the very short end, which affects the ionospheric conditions. And this one back in October 2022, the greatest of all time, the GOAT gamma ray burst, I was able to see quite a strong change in my good old Northwest Cape signal. So here's my measurement of Northwest Cape. Here's a satellite measurement of the gamma ray burst strength, so quite a good correspondence. Here's the gamma ray burst, sub-gamma ray burst point. Here's my path, so it's actually illuminated by the gamma ray burst. This measurement up here, quite different, and that's in the daytime hemisphere. And we've published a paper just recently in GRL talking about the difference between the daytime and nighttime propagation. This tells you something about the response here, tells you something about the time response of the ionosphere between day and night. And I've got another paper which is about to appear, which I've used some other measurements that I have, some other different paths, and I've backed out what I call the impulse response. It's the time response of the ionosphere to this gamma ray burst. So basically when a flash of gamma ray energy occurs, if it's in the nighttime sky, it's got a half-life of something like 15 seconds. So unless you have to be sampling quite quickly to see these things. And I'd actually done some calculations many years ago, kind of something similar. And so I log every second, which I'm generating quite a lot of data, but you've got to do these things quite quickly. You've got to cope with noise. So here's the gamma ray burst in some different paths. And if it occurs during the daytime, where it can be overwhelmed by solar flare effects, you don't have to be so quick. So I've learned a few things there and put some of that to practice in papers. So just to finalise now, I've given you a bit of an idea of some of the things I get up to at night or during the day. There are some of these really important organisations you can go and have a look at, and there are ways of contributing any and all of that stuff into these areas. And in fact, another really good source is the Radio and Electronics Association of Southern Tasmania. There are folks, you know, if you want to get involved in building radio gear or using radio gear, they're an extremely great local resource. We can get good tips on. I know that Lisa is involved, and in fact, Lisa's got a call sign. I'll get mine one day, but Lisa's beat me to it. And also, Facebook, I kind of keep an eye on meteor reports. There are some other good groups there where people are sharing information. So I encourage you to have a look at some of these things and to contemplate putting something in your backyard and trying to measure things that go bump in the night. Thank you very much. Thank you.
I'm a layperson and I'm still back at slide 3.
Right, yeah, good, that's good.
Solar azimuth and the Bunsen
Photometer.
And when we got up to the diurnal variations, ionic atmosphere, well, I'm lost. But I think you're amazing.
Well, I hope there's some little things in there that you can take away and go and have a research about and follow up on. I mean, the ingenuity of folks back in the day to actually even try and measure the brightness of something and say, well, how bright is it? And now we take it for granted because we do it with cameras and other instruments. We've come a long way. I couldn't have given this talk probably even 20 years ago. Some of those devices would have been well outside the price bracket of my hobby budget, and we're quite lucky now we've got consumer electronics to do those things. So I'm really excited to see what happens in the next 10 or 20 years in these areas. So, yeah.
Thank you. I did learn I don't need a hard hat.
You don't need a hard hat?
Medium gravity.
No, no. Hopefully we won't get hit, but there's a very tiny chance. But yeah, leave the hard hat off, and you can leave the big ears off as well.
A question born out of total ignorance. Is equipment, backyard equipment like yours, able to detect objects that intercept Earth's orbit rather than the atmosphere?
Not really, no. You need a radar, maybe, for that. So there are space radars that are monitoring the satellite constellations. They can see geosynchronous satellites. So probably something coming within geosynchronous orbit might be detected by a space radar system, and there's a new one going in Western Australia, which actually might be good for meteor detections. But not really, no. It's really, I guess, well, maybe. With the all-sky cameras, if it's bright enough, you might see, on individual images, you might see the movement. And something that's close to the Earth moves by quite a number of arc seconds per minute. I can't remember, there are some Earth-crossing asteroids coming up quite soon that will be moving quite rapidly across the sky. But generally, they're quite faint. They're 10th magnitude. There are some patrol cameras out there for meteors, particularly in Central Australia. They're probably capable of at least fainter than visual magnitude, that you might see some of those objects, but probably not. But camera's probably the best way to go, seeing something reflected. And in fact, I'm kind of keen for this nova to go off, as we like. Is it Corona Borealis or T Corona Borealis? I can't quite. Anyway, that should be coming up soon, and it's low on the sky for my camera, but that's a cosmic event, not an Earth crossing thing, but that's the sort of thing you might pick up with a camera.
Andrew, a slightly tongue-in-cheek question. Have you, over these 20-odd years, kept a graph tracking your total data storage?
Yes. Well, it's interesting. I could, yes, and it's kind of, luckily it's sort of plateauing because at the beginning, I guess I didn't have many systems running, and I wasn't logging particularly fast. Then there was a period where I realised I had to log faster, and I went up, and now it's sort of, it's just linearly growing. But of course, that's the thing you worry about is where do you put all this stuff and how do you keep track of it? And I must admit, when I was looking for some of my infrasound stuff the other day, I knew I had it on a hard drive somewhere. And back in the day, no, not floppy disks, thankfully. But yeah, there was a time when, yeah, terabyte was, well, just about enough to store stuff, and it's a few terabytes a year, which I'm having to invest in. And then the cloud now is pretty important. So I must say I do have stuff on the cloud that kind of is under analysis, but I do archive it. But look, I'd hate to lose it. But if I do, well. But I guess that's the other interesting thing. If people are interested in particular data sets, like I calculated it's over 10 million all-sky camera images, one a minute. Well, it's actually 2 a minute because it's an instantaneous picture, but a 1 minute stack. There are 10 million of those, and at about 170 kilobytes each. Yeah, starts to add up a bit. So yeah, luckily it's only linearly increasing at the moment.
I guess you sort of answered my question in answering Steve's question. So I was interested in storage capacity and that sort of stuff. And similarly, I assume over time, as costs have come down for storage and processing and whatever, as your so-called hobby has evolved, fortunately you've been able to stay on top of that. So I'll ask a different question, but along similar lines. Obviously, enormous amount of processing, I assume. So a lot of it's automated, I gather.
Yeah, I've developed little scripts. Luckily, it's nothing terribly computationally difficult. I guess it's trying to piece things together. It's always the tricky bit, you know, time series of things. But yeah, Copilot is my friend at the moment. It's helping me write some Python scripts to try and do something with these things.
And so how much do you need to actually look at? I mean, do you suddenly go, oh goodness, there was an event happened either through the media or through your colleagues or whatever, or do you literally old school go, okay, what happened last night or what happened yesterday?
Yeah, I'm not keeping up night to night. I'm really looking at events that pop up from time to time. Yeah. Somebody saw something. Keep an ear out on the radio. Somebody heard a bang. I'll go and have a look at that. I do have, I make some movies of the All Sky Cam stuff, and that's probably the most I look at. Is I'll look at a night of that every so often.
Yeah.
But, even in retirement, I haven't got time to do that.
Well, I wondered that too, in as much as, do you actually get time to eat?
Well, I'm not like Grote Reba. I'm not there logging every single data point by hand. I was reminded of that. I went out to the museum the other day again, and that's how Grote made his maps of the sky. He kind of actually physically logged, the galvanometer value each 5 minutes or 1 minute or something. But I pick out events, and I've got 4 scientific papers that have come out of this stuff. So because I've got experience in writing these things, I know what I'm looking for. But it's interesting, there are still opportunities for folks to write papers, and getting involved in these folks, they have a network, and if you're not a scientist, you can become an amateur scientist and write stuff up. They're publishing in good journals, some good papers there. And even just being associated with AAVSO, it's important, having a data point in there.
All right, we've got time for one more question from Dallas, but if anyone else has got any other questions, Andrew is happy to have a chat with you at the break.
Yep.
Yes, I was in the Picnic Basket Cafe in Taroona and talking about auroras, and there was a gentleman there stood up and said, "Oh, I'd like to know more about auroras," but then he started talking about how different stars can trigger other stars to react, and he said the 2 pointers are an example, and they affect the sun. And I was very interested in that, and I said, well, I'll have to look it up. And he said, well, you can't look it up, it's in my head.
Right.
So, and here's a university, part-time university professor, he's retired now, a lecturer, and he seemed very convincing about it. So, do you know anything about stars, like maybe pulsars or triggering?
Certainly, things like pulsar winds, jets from objects, but I'm not sure about the pointers. Maybe Stefan might have an opinion here. I guess, we're all moving through space together, and some of us are moving faster than others, and some of us will catch up with others, I suppose, but I'm not so sure about that sort of connection over that distance that has any significant influence on our solar system, for example. But, we need to think more carefully about some of these things, so I wouldn't dismiss it, and, if that person had some good reasoning, I'd be interested to hear it. Yep.
Okay, Andrew, it's been a fascinating talk. I'm totally blown away by your problem-solving ability, just to put all that equipment together and make it work. We know what it's like with telescope equipment to try and get things to work. You're blazing new frontiers to get machines to talk to each other.
Yes.
Then you actually got to interpret the data, and that's probably even the more difficult, I would imagine.
Can be.
Yeah. So, I mean, to me, you're the eyes and ears of Tasmania, honestly. You're always listening, always looking.
I hope I don't go to sleep. That's right.
You've got AI to help you now.
That's right.
So, yeah. So, on behalf of everyone, thank you very much, Andrew. And and as a token of our
thank you very much.
gratitude, Gennady, I wouldn't leave Tasmania without having a taste of that.
Oh, very nice. That's nice latitude there. Thank you very much. Yes.
42 degrees, yeah. So we're going to have a break. If you like to volunteer for the Night Sky Explorer course and haven't already got the information, please see Richard at the break. If you'd like to come to the dinner, 14th of November, come and see me. Thank you to whoever brought the supper tonight. Some lovely goodies up the back. And make sure you've got your ticket in the lucky door prize. Okay, have a nice break. And Richard will be following.
Can you hear? Oh, when I tap that, can you? Yep, that's good. Yep. Better leave my keys there. No, no. Okay, so we'll kill the lights. Okay. Thanks, Matt. If you could. Evening, everyone. For those who don't know, the Cygnus Loop, photographed with a dual narrowband filter, very, very low in the sky, looking through murk. I can't remember how high that was, but it was only about 10 degrees, I think, or something like that. Not much. So you're fighting the atmosphere at that low elevation. All right. So I'm going to. Hopefully this will work. Yes. Voice music. It's not me. No. Okay, so just a quick presentation. I'm sorry if I'm going to speak quickly. Just a few things. I'm setting everything for 10 o'clock or 11 o'clock at night, 30th of November. So, you know, you've got about 2 hours of rotation time there from now. So remember that. The stars rise 4 minutes earlier every day. So by the end of a calendar month, it's about 2 hours difference. So you've got to allow for that. But anyway, I've allowed for that. So what you're looking at is the 30th of November. So if you look over here, there's a couple of interesting things. For those of you who like to look at Uranus, it's quite bright at 5.7, but of course it's a tiny thing through a telescope, and you need 2 or 3 meters of focal length to get a decent, even to get a good disk. So it's very small. But I want to concentrate over here on Triangulum, which is very low, like all the things I've been taking photos of lately. They're very low on the horizon. Now, you might have a quick look there. You'll see to the left, M33. Now, the Triangulum galaxy, it's a picture I took last year. I can't remember when I took it. Is I think it's about 2.5, 2.6 million light years away. It may be slightly more. And it's less than 1 million light years from Andromeda. So there may be some tidal interaction between the two, but it's quite a good object to take photos of for those of you interested in photography. And I imagine, we're at Font Hill and places like that, you would get a view of it through binoculars and things. You see a little smudge. It's bright enough to pick up. Whereas in our skies, especially our Border 4 sky out of Mount Pleasant, you'd have to really, you need a telescope or something to find it, a pair of binoculars. It's certainly not a terribly bright object. Down here, Caldwell 28, I'm going to talk about that in a moment, is a lovely star cluster. Now, I'm sort of getting away from the usual targets. There are a few things here that might pose a challenge, but this is a beautiful star cluster. Open cluster Andromeda, 5.7, that's not too bad. To look at a gigayear in age, 75 arc minutes across. So I don't know how many of you have actually seen that, but there's a star cluster that I haven't talked about before. That's the particular picture there is a simulation on Stellarium with my telescope and a 24mm eyepiece, a teleview eyepiece, which gives you 34 magnifications. So it's a decent cluster to look for. There's a picture of it down there. And now a challenge, a bigger challenge. At the tip of Triangulum, you'll see M33 over here, the galaxy. If you look up here at this little area, there's a pair of interacting galaxies. Now, you might remember at Font Hill, I spoke about NGC, I think it was 1316, the interacting galaxies. Do you remember that? We had a bit of a chat about that in Fornax. Well, here we are in Triangulum, a pair of interacting galaxies, but this one's a faint one. So that star cluster there is Colander 21. And next to it is this really interesting pair of galaxies. So something for those of you who are keen photographers with your telescopes, that might be worth looking at. I imagine that would be extremely dim I think it's magnitude 11.5 to 12.2 for those two galaxies. So well beyond, except the larger telescopes. So a difficult challenge, observing-wise, but not photographically necessarily. So keep an eye out for there's a challenge. So now I've moved slightly to the east because we all know about Orion. I'm not going to talk about Orion, but I am going to talk about these two star clusters that you might be familiar with, the Hyades and the Pleiades, which are coming up now. Now this is at 11 o'clock at night. I've allowed for a bit of rotation because that's when Orion's rising quite late still. But this is the constellation to look out for in this area because there's still a lot of interesting material here to photograph. Now the Hyades and the Pleiades make a bridge. I think they call it the Golden Bridge or something because they're either side of the ecliptic, as you can see. And so they've been given this nickname. Andrew mentioned Aldebaran earlier. There's Aldebaran over here, about 67 light years away. And I think it's about 6.4 billion years old. So it's in red giant phase, left the main sequence and is burnt its helium, hydrogen to helium. And so it's swelling. And the same thing that's going to happen to the sun, basically. And even though it's quite large, it's, I think it's about 45 times the size of our sun, something like that. It is actually only slightly more than the mass of the sun. So it's a puffball, low density. Anyway, so the Hyades. Now the Hyades are very interesting because they're quite bright. Now the Hyades and the Pleiades are, according to Greek mythology, half sisters. Daddy was Atlas. Pleione was the mother of the Pleiades, hence the name Pleiades from Pleione. I'm not sure who, I think it was Hyas or somebody was the parent, I forget the parent of that, some nymph was the parent of the Hyades. You might remember the wonderful poem by Lord Tennyson, when the rainy Hyades vexed the dim sea, when there were storms in the northern hemisphere, the Hyades are known to bring rain. So in April or whenever. So the rainy Hyades, that's where that comes from. Anyway, there are only about 5 stars in the Hyades cluster that we pay attention to. There's a little bit of an overlay. Up here you've got Prima, number 1, Secunda. Then over here, Tertium and Quattrum, which are like 3rd and 4th, Theta Tauri. And down here is Ain. Ain is the bull's eye, the right eye of the bull. And down here, you've got Aldebaran. Aldebaran has nothing to do with the stars around it. It's a different, not in the same area. This is about, I think they're about, from memory, the closest, this is the closest, by the way, the closest open cluster to us. And I think it's 153 light years or something like that. So along with the Southern Pleiades, the Northern Ursa Major group, and a couple of others, they're very close, open clusters. The Pleiades is another, of course, which is about 444 light years away. So, beautiful object to look at. Have a look at Aldebaran if you're interested in seeing a lovely orange colour that it has. I think it's a K3, you know, Andrew? I think it's a K3 star. So it's a giant, but it's very yellow, very orange yellow. All right, so now moving over here for a moment, if I just expand that, that's a lovely picture of the Hyades. I forget who took that, but you can see Aldebaran showing a lovely reflective telescope there. So keep a lookout. I've mentioned the quotation from the Iliad there. Mentioned the Iliad. I mentioned the quotation from Tennyson's poem, "Through scudding drifts, the rainy Hyades vex the dim sea." Beautiful poem. Best poem in the English language, in my opinion. But anyway, the fact that I taught it as well in English literature made it even better. All right, so now, by the way, if you get lost in this area of the sky, one thing to remember, I'll just go backwards a minute, is you can always tell when you've got Orion, you've got his 2 dogs, Canis Major and Canis Minor. Canis Minor is piggybacking on Monoceros. The Monoceros is the unicorn. So this is the unicorn. It's facing up this way, and Canis Minor is on its back, basically. So you can't lose that. You always see this star Procyon, which is very bright. And of course, Sirius up here being Alpha Canis Majoris. All right, moving on. So some interesting things to happen in the night sky there shortly. There's a view through a pair of binoculars of the Hyades, so quite a good view. Get the whole thing in, 7 by 50 binoculars. You don't need anything else. You lose the whole shape otherwise once you start magnifying. And there's a beautiful, I think it's a Hubble image, which we all aspire to. It's a beautiful bunch of stars. And of course, as we all know, featured on the bonnet of all Subaru cars, because Subaru in Japanese is the Pleiades. Anyway, now here's a view, excuse me, at a magnification there of 23 times to get there, because it's quite a broad area, several degrees. I forget how many degrees across there. That's nearly 3 degrees in width. And a beautiful object to photograph. You all know how the Pleiades, of course, did not get born here. They were, that cluster, all those stars have the same directional motion, similar velocity, so they were born elsewhere, and they have simply drifted into this cloud of dust and lit it up because they're young stars, and they've lit the dust up with their colour, scattered blue light. Excuse me. I don't know if you know the names of them, but Atlas and Pleione are always at the back. In actual fact, if you're looking through a telescope, it's pointing the other way, but in the northern hemisphere, everything is reversed. Up the top there, I think, is that's Maya, and I think that one's, what's the famous one? Merope and Electra. Excuse me. Wow. Dry throat. Facing east, a little bit of a magnified view of what we're looking at. Does anyone know what I'm pointing to there? Sorry? Oh, look, if I had a chocolate, you'd get it, Steve. Excuse me. It is M78. M78 is the Casper, the Friendly Ghost Nebula. And I'll show you a picture of it shortly. A beautiful thing. I've never looked at it through a telescope. Have you looked at it through a visual observing? Quite bright, Steve? Yeah, the blue, as you'll see in a moment in the photograph, there's a very bright part to it. There's supposedly a reflection nebula. Oh, thank you very much. Thanks, Brenda. Need to slurp a bit of water, excuse me. Anyway, so the Dolphin Head Nebula, things to look at up here. That star there in the Dolphin Head is Udra, which is just up there, that bright star. But the star that caused this is EZ Canis Majoris. You probably can't see it there because my picture's too small here, but it's that star right in the middle of this. I think it was about 9,000 years ago that this thing ejected all this material, and its ultraviolet light is making ionizing all the gas about it. But that is a beautiful object to photograph. I'm not sure visually that you'd see anything, even with oxygen filters and whatever. It would be very hard to pick. But anyway, there's an interesting, beautiful, well-known cluster here, M41, and there's a lovely picture of M41 that you could look at through a telescope, any telescope. And over here, one of my favourites. Now, Steve introduced me to this years ago. It's called, alternatively, NGC 2477. It's called the termite hole cluster, is one name for it, or the electric guitar. Now, I can see an electric guitar, but I can't for the life of me see a termite hole. But anyway, it's supposed to be, it's a beautiful, beautiful object. I've looked at it through a telescope and it's dazzling. It's really worth looking for. So that's in Puppis. So next to the star Naos, I think it is over there. Yeah, there's Naos. So if you find Naos, we're very close here to Vela and the False Cross and all that area of the sky. But anyway, so there's something to look out for. Burnham, I think, said, one of the most beautiful clusters in the night sky. For those of you who have Burnham's Celestial Handbook, have you still got yours, Andrew, by the way? I haven't got mine. I don't know what I did with it. Yeah, beautiful. Sorry? Yeah, I lost track of it. I don't know what I've done with it, but I think they're still in print. Yeah, so might be able to get them. I love his descriptions of things. Anyway, so there's electric guitar cluster. It's a long way off, 3,600 light years, about 300 stars, but it's almost the width of a full moon. So put that in your eyepiece. Beautiful. Put that without blinding yourself. Now, a shot I took of the Seagull Nebula. Now that's about 110 light years across. A beautiful, beautiful thing to look at, but also something that's a very long way away in Monoceros. Now we all know Monoceros has got some interesting things, because over here on this side of Monoceros we have the Cone Nebula and the Christmas tree cluster and everything else all in one field. And it's one of my favourite objects, and I hope to photograph that with my new telescope when it gets here one day. And over here, of course, is the beautiful Rosette Nebula, which I'll show you a couple of pictures of in a moment. So Monoceros has got some interesting things to look at the moment. There's a picture I took of the Rosette Nebula. Yeah, and the cluster in the middle, I forgot, was called the Harp cluster. I didn't realise that. Any of you know that? The cluster in the middle, the stars that were born in this are pushing the gas away from them. So now there is Casper, the friendly ghost, M78. A picture I took, I don't know, last year, year before. I always wonder about it. It's a strange thing, but this is not the whole thing. But look at this area down here. Very interesting area of activity. So those of you with longer focal lengths might like to concentrate on this part of the nebula. I think very interesting. Yes, it's a really bright. Yes, absolutely. Anyway, magnitude 8.3, 8 by 6 arc minutes. So it's not gigantic, but 1,350 light years away, and visible as a hazy patch in telescopes. So you might like to look out for that, just down from Orion's belt. Remember that? Just down from Orion's belt, down from Alnitak. And there's a frame up of it using a APS-C sensor and a focal length of about 873 on my telescope. So you can fill the frame with that. And there's a lovely, I think that's a Hubble image or one of those, I forget which one. So, sorry if I'm speeding up, but the interesting thing about this is M78 through the Euclid spacecraft. Did you, Euclid, anyone heard of Euclid? So that belongs to the ESA, the European Space Agency. And this thing has been cataloguing. Look what you can see when you look through dust, basically. And you see all these wonderful structures. I think this is an amazing image. The VIS and NI, near infrared, I suppose that means, cameras reveal over 300 new objects in the field of view. So what you don't see in visible light, infrared will certainly show you. And there's another picture, and that's through the Vista telescope from Paranal in Chile, La Silla's observatory there, the ESA observatory. If you blew that up, you'd be amazed at what's in there. That's just, I took the low-res version, but the high-res version is really fantastic to look at. Now, here's the electric guitar cluster close up so you can get a decent view of it. You can see lots of red giants, beautiful thing to look at. So note that one down, 2477 in Pappus. A close shot of the seagull. Now the seagull, this is a frame up using, what is it, my telescope, and about 2 degrees across with a wide field sensor, a full frame sensor. It's quite big. I think it's 50 or something light years this way, 110, 120 or something like that way across, but a beautiful object to look out for. That's a Vista image again. And what are we looking at? The cone. Now this has just, I just love this. I think this is the Hubble image, I'm trying to remember. So here's the Cone Nebula. Now if you look here, if I just take your eye, follow the red dot. I'm sorry about the latency in this thing, it's driving me cranky. But if you look down here, you can see the shape on, I'll probably use my hand. You can see the shape of a Christmas tree. The triangular shape, called the Christmas tree cluster, but in infrared, you can see other things in here, which I'll show you shortly. The snowflake cluster, which only shows up in infrared. Well, mostly in infrared. Down here is the fox fir. Can you just make out the fox fir? Fox fir nebula, beautiful thing to look at, and I'm going to show an image by one of our members, which is really fantastic of that. So, that's the La Silla Observatory. Now this is, an infrared image of it. And if you look over here, The same thing, put up the same way. I think the cone is down here somewhere in this dark area, but here's the snowflake cluster, which is not visible on there, but that's the snowflake cluster. I just love what infrared can show. And guess who took that? That is by Eugen. And I love the colour. Eugen's not here tonight, but a beautiful image he's taken of the whole field. And what I like about it is it's different colour. It's very different from the usual H alpha red light. So lots of interesting structure there. And you can see the tree and the base of the tree, where the crown of the tree is, the trunk. You can see that very bright star there. I think it's S Monocerotis from memory. And then you've got the triangle of the beautiful triangle. And then you've got another bright star. I forget what that one's called. And the cone and the fox fur is down here. A pair of eyes. If you look at a close-up of that from a Hubble image, you'll see it. It does look just like a fox fur. Quite an amazing area. So there's something worth photographing. 20 arc minutes across that, 2/3 of the moon width, photographed by Eugen. Now, up here, Canopus, some markers for you in the south. Canopus is about 320, 340 light years away. It's a giant star. Over here, you can always pick, if you've got Canopus up here, somewhere around the area will be, forming a triangle with the South Pole, will be Achernar. Achernar is out of the field of view up here to the right of the meridian. So now you've got the two Magellanic Clouds as markers. Now we were saying only the other day, the Magellanic Clouds were really visible years ago at Mount Pleasant, naked eye, no problem. But now you have to strain on a cloud, on a moonless night to find them. And you really have to squint and search. So I think our sky's drifting from Bortle 4. It'll probably be Bortle 5 before long, with all the light pollution, unfortunately. Anyway, I wanted to show you there's a meteor shower coming up in December, the Puppet Velids. Andrew was talking about meteor showers. About for the first 2 weeks, the zenith hourly rate is 10. So 10 meteors an hour. Under ideal conditions. That's right. And if the moon's out, I'm not sure on that night, trying to remember the moon was out, you mightn't, on the particular 30th of November, you mightn't get to see them so well. But this is facing south at 11 o'clock in the evening. And down here, now you might remember, what's this famous thing I'm pointing out to you here? What shape is that? The false cross. Right, so if you remember, Marrakeb is Kappa Velorum, Delta Velorum, Epsilon Carinae, and Iota Carinae. And next to Alcifina, Delta Velorum, there's a beautiful star cluster. I'll just show you. That's the false cross, asterism. Asterism because it's not a constellation, it's just a shape we've picked out. Now, there, that cluster, does anyone know what I'm pointing to? Whoa, here's a man who's observed the sky. The Omicron Velorum cluster. That's Omicron Velorum, and it is a beautiful cluster of stars. Not so many stars, but very, very pretty. And in fact, I can get up in the morning, so if I look out at the false cross, I can see that naked eye. There's no difficulty whatsoever in picking it out. It's really bright. So there's something worth looking out for as you face south. Magnitude 2.5, 50 arc minutes across for the whole group. And about 574 light years away. So that's the other, in that group of open clusters I mentioned to you, that's in the top 5 or 6 clusters, closest clusters to us. Another shot, I don't know who that, if it's Hubble, I'm not sure, I don't think it's Hubble, I forget where that was. But I thought I'd show you that picture. Now this is a familiar sight, and now we've talked about this forever. The Eye of Sauron. No, the Helix Nebula, worth looking at one last time because we're facing west now. So the Milky Way is setting. We're actually gradually, as we go in our orbit around the sun, we're facing away from the centre of the Milky Way through the Orion Arm. So we're looking out at fewer stars. We're not looking at the centre of the galaxy anymore. The galaxy is setting in our western sky and will be come around in autumn again. But for the moment, it'll be in the daytime sky, so you won't see it. So this is your last chance to look west and have a look at all those objects before they disappear. And in fact, I think it's this month, October to November is probably the last chance you'll get before it actually goes below the horizon. And you won't see it again. And you'll miss out on the Lagoon Nebula, the Trifid Nebula, and all those million things we've been talking about before. So that's an infrared image. I think it's a Spitzer image. And that's why they call it the Eye of Sauron. I think people looked at that and thought, well, that looks like, that's a bad case of red eye, isn't it, or evil eye. But look at the structure in it. And you can see those things we call cometary globules quite clearly in the middle. Now, don't forget, these are telescopes worth many millions of dollars, right? Now, here's a picture by Greg England, our top photographer, and he's taken that, and if you look at it, or you can't see from there, he's picked up as good a resolution as that thing in the middle of this telescope. And this is a 170mm Maksutov Newtonian telescope. So, so Greg is one of these people who can take the best out of the data and bring it out and has the most amazing images, absolutely stunners. And you all know he got a highly commended in the, what was that contest? David Malin Awards. Yeah. He deserved the grand prize, I thought. His photograph was just stunning, Anyway, he's a very accomplished photographer. And that's a monochrome RGB, H-alpha, sulfur. What else do you have? Something else. And oxygen, of course, yeah. So that's by Greg. I thought I'd show you that. Now, of course, Saturn's up in the night sky, crossing over the meridian and heading into the west. And so if you want to have a quick look at Saturn, if you do a close-up, oh, sorry, one more picture of that. I've turned that upside down to show you. That's a APS-C camera, and yeah, quite a high magnification with my 6-inch refractor. I can just, that's about the biggest image I've got without changing the camera. But you can get a decent image of the helix with most telescopes. Now, so Saturn's looking like that at the moment on the 30th of November. You can see some of the innermost moons, and Titan, of course, is always easy to see. How many do you spot at all? Yourself, Steve, do you see? 6, have you? Gee. Yeah. Yeah, because they're all constantly moving, of course. So, yeah. Anyway, so that's a view of what you'll get on the 30th of November if you look at Saturn. The rings are almost edge on. Now, last frame. What is the star? It's my favourite star, but I put it up there because I talked about it several years ago. I'll give you a clue. It's in Monoceros. In a ficus, sorry, not in Monoceros. Can you remember this? No. Is anyone no? Well, this star is a beautiful star, Zeta Saik or Zeta Ophiuchi. That image is, this star is 3 million years old, 8 times the size of the sun, 20 times its mass, and this bow wave or shock wave, Andrew talked about shock waves and things, this shock wave is a half a light year in front of the star. The remarkable thing about the star is that it's going to be a supernova before too long, I suppose, a few million years maybe. But it's the rotational velocity of that star that is amazing. It is nearly breaking up. It's spinning at 400 kilometers per second. So it's at the actual, what they call the physical limit before the star can literally fall apart, tear itself apart. And the poles, like all these stars that spin fast, I think another example would be Regulus. The pole and the equator have different temperatures. The poles being hotter and the equatorial regions being cooler by 9,000 degrees. This is a 36,000 degree star, so it's about 6 times hotter than the sun. But I love it because of all those interesting things and the fact that it's a runaway star. And their explanation for it is that, contrary to the original theory, was that some stars came nearby and shifted out of its orbit, which often happens because there are lots of free stars moving about, runaway stars. This is a runaway star. But This one was probably a part of a binary star system, and the primary blew up. It actually, this thing drew material off the primary, and then there was the primary itself went supernova, and they were expelled from the same binary system. So this star went one way. The remnant of the primary star became a pulsar, which they have found, and they say that this star was expelled from it at great velocity. It's travelling at 108,000 kilometres an hour, roughly. But I just find that a beautiful image because it's infrared. And there are different frequencies. The greens, I think, a higher frequency of infrared, and the red is a longer frequency of infrared. Yeah. Yes. Oh. The pulsar that belonged to it. By examining its velocity and direction, yeah, they say they were once related. So, but a stunning thing, and I think it's wonderful. Anyway.
Richard, is that the result of what happened at Bellway?
Yeah, well, that's about half of it, yes. So what it's doing is, I don't think it's just the radiation. I mean, and it could be the effect of the spinning. Imagine the spinning of that star too, the spin. I'm sure all these things have an effect on the surrounding interstellar medium. But this stuff was all here, but it's just been caused by the plasma, the radiation from the star has hit this and pushed it in front of it. Just like, in a ship, you've got the bow waves. Yeah, so you get that compression. And of course, they all collide. Anyway, I love that star, and I love that picture. So there it is in a ficus. Got a picture on the left there of ficus. It's the middle star. There it is there. It's called, sorry about this, Saik. See that one there? You might remember, some of these, I forget that one there. Got an unusual name. Ras Al Hag is the brightest one. Here, Yed Prior, Yed Posterior, and Subik at the top. I'm trying to think what that one is. Oh, Cabal Rai. Yeah.
That's yeah, so that has a really high proclamation.
Yeah. Yeah. Yeah.
Image than over a couple of years.
I would love to see if anyone using an infrared camera would be able to pick up that dust. Because, I think Andrew was saying his camera was infrared. I mean, I'd love to see what would show up from an amateur's point of view. Anyway, so that's it, folks, and there's the star. Yes, guess where it is? You've got Scorpius in the left, and a ficus is down here to the right, just to it, because the ficus goes into Rho Ophiuchi. The legs of the serpent bearer disappear into Rho Ophiuchi. So it's right next to it, but it's all setting. Be gone soon. So that star, this is your last chance to have a look at it. It won't be around much longer. Then you'll have to wait till probably autumn next year. Yeah, so that's it. Thank you, folks.
Have you got a cartoon at the end?
No, yeah, I feel wrong.
Yes, no, not today.
Okay, we did get a cartoon, but we have got a thunderous applause for Richard for a beautiful presentation. So just to...
Yes.
Very good. Okay, so just a couple of thank yous. Well, firstly for our two speakers tonight, fascinating evening. Big thank you to Matthew, who comes all the way down from Oatlands to open up and set up the room. So thank you to Matthew. Thank you. And also Lisa, we've had an incredible range of speakers this year, I think you'll agree, and that is not easy to set up, and Lisa's been instrumental in making all this happen, so thank you, Lisa. So with that, I hope you have a good evening. Just in case you don't know, if you've still got something to say and you haven't had anyone to say it to, come to McDonald's and have a coffee with us after we finish here. So, good evening, everyone.
like that?